So on the note page in your packet, we're going to try to help you guys figure out there are 8 different situations where you're going to feel G-forces, and we're going to try to break it down for you. So the first thing is, let's just sketch out for you really quick, what is a G-force? If you're just sitting on your chair, or you're on the Batman or Raging Bull or whatever, tell me the 2 forces that are acting on your body. You guys remember? There's a pull of gravity, that's called weight. And you know what's weird? People get confused. They think that, like, you know, gravity pulls you up or sideways sometimes. It never does that. Gravity always pulls you down. But on a roller coaster, as you fly through turns and loops and whatever, you feel different G's because of your seat pushing on your body. So, again, how come you don't fall? It's because of which force that pushes upwards, perpendicular to the support surface, called the, everybody, normal force. So here's how we can define G's really simply. G-force is really the ratio of the normal force on your body compared to weight. And normally you feel 1 G because you just experience the normal pull of the Earth's gravity. If you weigh 150 pounds, your seat is pushing up on you 150 pounds, right? If you weigh 200 pounds, then your seat pushes up 200 pounds. Wouldn't that be weird if you only weigh 100 pounds and your seat shoves up on you on 200 pounds? Okay, you would like go flying in the air. That'd be bizarre. Okay, so it's kind of cool that it just works out that way. So what I'm going to do is I'm going to show you guys one of the hard ways on how to derive G-forces, and then we're just going to do this. Okay, so this you don't have to put in your notebook. I just want to show you that this is... So the first kind of G you can feel is called the lateral G. This is just when you're sitting in the cart and then it takes off. Greatest example of lateral G's is the V2 at Great America. It uses magnets to shoot you forwards. Okay, and all it is you take your acceleration and you divide it by 9.8. And your acceleration is just your final minus initial velocity over time. So for example, there's only like 4 sports cars, I think, that can where you get actually over 1 G in terms of lateral acceleration, including the Bugatti Veyron. It's 0 to 60 in less than 2.7 seconds. So it's a little bit over 9.8 meters per second squared. I think it's in the 10 to 12 meters per second squared range. So you're getting like anywhere from like 1.2 to 1.3 G's sideways. Okay, so on a bank turn, you feel sideways G's because you're getting ripped into a circle. So you ever notice, like, when you're going through a turn, you feel like you're thrown to the outside? I'm talking about of a turn there? And all it is you naturally want to go in a straight line. You need a centripetal force from the roller coaster cart or your seat belt or the car door or luggage, right, when you're pushing somebody to push you in the circle. And all you do is you find that centripetal acceleration, V squared over R, and you divide that by... Now, let me do a nasty one for you here. And then we're just going to use a table to make your life easier. First question, common sense. When you go down a hill, do you feel heavier or lighter? You're going to feel lighter. Here's how you come up with the G-force equation. You ready? G's is the ratio of normal to weight. When you fly over a hill here, your seat starts to drop out from underneath your butt. Now here's what's cool. All of these curves are parts of a circle of a certain radius. You see that? As a coaster designer, you get to pick that radius of that turn. Either a sharp drop or a gentle slope there. The net force will be the pull of gravity, weight, minus the normal force trying to hold you up. If we rearrange this, because G's is normal to weight, we have the normal force is equal to the weight minus the net force, because we're rearranging our net force equation. And the net force, in this case, is your centripetal force to pull you over that circle. Gravity pulling you down that circle with the seat trying to hold you up there. So now we have normal equals weight minus MAC. If we substitute this into our G-force equation, which is normal, which is weight minus MAC over the weight. Then we expand, weight is mass times gravity. One cool thing to notice, all the masses cancel out. So in other words, if you get a bunch of football players on a roller coaster and then a bunch of like little 6th graders or whatever, it doesn't really matter how much mass is there in terms of G-force and velocity. A heavier thing and a light thing, they fall at, this is funny, this is my 8th grader, my orange monkey here, right? They're going to fall at the same rate, heavy versus light. Okay, so if all the M's cancel out, you get G over G, which is 1, minus AC over G. So in other words, the final equation is equal to 1 minus AC. Now, how many of you guys think that if every time you have to solve a G-force problem, you have to derive the equation, it would be a real pain? Is that a real pain? So what I'm going to do is, instead of making you derive it every time, we're just going to come up with the G-force equations and then use this table. And all you got to do is match the table to your coaster design so that on your final coaster project, it's pretty easy then to do the G-force calculation.